The first problem in question A asks us to write the balanced equation to the oxidation half reaction. And what you're given is Zn solid reacts with CO2 plus to produce Cl. So from this we can assume that Zn is the reactant and whatever it turns into is the product. And this product is Zn2 plus. And so we need to add 2 electrons to balance out the charges of this half reaction. And the second problem asks us to write the balanced net ionic equation for the overall reaction. And what's given is CO2 plus turns into Cl. So we know that, And the reduction reaction would be CO2 plus 2E plus Cl. And then those electrons would cancel out. So then it would just be Zn solid plus CO2 plus turns into Zn2 plus and Cl. And the third problem asks us to calculate the standard potential, E degrees, for the overall reaction at 25 degrees Celsius. And as you can see, I wrote down both of the oxidation and the reduction reactions. And so I found both of these E values from the textbook, and so you can backtrack that. And the E for the oxidation was 0.76 volts, and the E degrees for the reduction was negative 0.28 volts. And if you add them up, E degrees is equal to positive 0.48 volts. The first problem in question B asks us to determine the value of the standard free energy change, delta G degrees, for the reaction at 25 degrees Celsius. And to do this, we need to use the equation given to us. And so the equation for delta G is delta G is equal to negative NFE degrees. And so if we just plug in some values, N is equal to 2, and F is Faraday's constant, which is 96,485, and the E degrees, which was given to us, is 0.55. And if you multiply all of those together and divide by 1,000, because this is in joules, you get negative 106.13 kilojoules. And the second problem asks us to determine the value of the equilibrium constant K equation for the reaction at 25 degrees Celsius. And I did this by using the equation. K equation is equal to E to the negative G divided by RT power. So I substituted the value I got up here, which was the delta G, and I divided that by R, which is 8.31, and times that by the temperature. It was 25 degrees Celsius, but you have to add 273 to get it into Kelvin. And if you do that, you end up getting 4.13 times 10 to the 18th. And problem 3 asks us to determine the value of the standard reduction potential, E degrees, for the half reaction below. And so we are given 2 equations to use. And we flip the top one to get a positive E degree value. And if you do this, you cancel out the 2 H2O's, and that's why you don't see it in the equation below. And the O2's combined make 2 O2. And if you subtract negative 0.55 from 1.23, you end up getting 0.68 volts. And question C asks us to calculate the maximum mass of Cu that can be deposited by a direct current of 100 amps. Okay, so to start out, we put 1 hour on top, and we have to get this into seconds. So 1 hour is equal to 3,600 seconds. Then you multiply that by 100 amps. And 1 amp times 1 second is equal to 1 coulomb. And 96,485 coulombs is equal to 1 mole of an electron. And there are 2 moles of electrons in this particular equation. And then for every 2 moles of electrons, there's 1 mole of Cu. And the molar mass of Cu is 63.55 grams. So if you multiply all that together, you end up getting 118.56 grams of copper.